Hi, I'm Tim Sweeney, and this is my final project, final video for ENPM701, Autonomous Robotics at the University of Maryland. I'm taking this course in the spring of 2025, and it was a great course, a lot of fun, did a lot of good engineering work, and I'm going to show it off to you today. So enjoy. All great engineering videos need a time lapse. So here I am assembling the robot. We got the frame for the robot from DF Robotics. We got the Baron model that comes with all the parts like the motors for the wheels themselves, the chassis, and then we added to that a bunch of other off-the-shelf parts like a battery pack for motor power and then a battery pack for our Raspberry Pi power. And we keep those separate on two different power domains so that the Raspberry Pi gets clean power. We use Pi Camera 2, which is an 8 megapixel camera. We have a ping sensor for distance detection. There's an H bridge on the robot for controlling motor speed. Here you see me putting together the IMU, soldering it together. We use that for orientation detection. And then here you can see that we programmed an Arduino Nano to collect that information off of the IMU and pass that to the Raspberry Pi. Throughout the course, we had a few assignments where you need to do object detection, which is what we see here, and then object tracking, and image annotation. All very important stuff, and which leads us into the main code. Okay, so this is the code base of the robot. You can see that I'm SSH'd into the robot right now. I'm running this in VS Code, which was a huge help in this project because being able to use VS Code instead of Vim or whatever other IDE comes pre-installed on the Raspberry Pi. I can just work on my MacBook and then SSH in and get all the benefits of VS Code. So once I figured this out, this was a huge benefit. But here we have our main module. This is where all of the code for the robot comes together. I'm going to put up here a block diagram of the state machine. I'm not going to go through every little bit of this, but just basically how it works is the robot state machine starts. We select a goal. We can see our list of goals here. We cycle through the 9 blocks that are in the arena, 3 red, 3 green, 3 blue. And we select our next goal, look for a path to the goal. If we can't find that path, search for one. Drive the path, collect the block, drop the block off at the collection area, and then repeat until all of the blocks have been collected. And then at the end, we start a cleanup routine where we look into the map and try to collect any extra blocks that we might have missed, accidentally as we were running through the main part of the program. There's a lot of interesting stuff going on in here that it would take too long to get into, but a couple things, is that we're running 4 threads in the program here. We have our main thread, and then in the background we're running a thread for the IMU to collect the heading of the robot. We have a thread running for the odometry and just determining how far the robot has rolled. And then we have a thread for drawing the world map. So in a moment here you'll see as the robot moves through the world, it updates its world map of block locations and where the robot is located within the world, the heading of the robot. And that's pretty resource intensive. So, we start up a new thread so that we're not blocking everything else while that's going on. This is the vision module. This is where we instantiate the camera, do all the computer vision of, masking out blocks, conversion to HSV space, placing bounding boxes around blocks. converting, positions in robot frame of reference to world frame. And as a part of that, we had to collect, this information, do this test, collect this data. And this is showing us the height of the bounding box of each block on the left to how far away it is on the right. So we came up, after collecting the data and fitting a curve to it, we came up with this equation, which we use to determine how far away blocks are from the robot. And I think it works pretty well, actually. Better than I thought it would. When it correctly identifies the block. That was a recurring issue for me, was correctly identifying the block just based on the lighting of the room. And then after all of the code is written and running on the robot, the name of the game is just test, test, test. And just try and shake out as many bugs as you can. So you can see here I actually tore apart my apartment and mapped out the arena, the Grand Challenge arena. It's slightly smaller because I didn't have the space, but this arena here is 9 feet by 10 feet. And I would use the 3 blocks that we had to attempt to recreate as best as possible the conditions that the robot would be working in. Apologies for the shaky cam. I hadn't really expected to speed this up so much, but in the interest of time, it's probably for the best. You can see that the robot collected all of the blocks so far, and here actually we have the view from the robot and the world map as it updates. You can see it drives around, constantly collecting videos and saving them to a video buffer. And you'll see that there's a lot of noise in the video. Noise being erroneous identification of blocks. This was a problem in my apartment because just, the glossy floors had a lot of reflections, and I would constantly be identifying blocks that weren't there. But to account for that, the algorithm figures out the orientation of the robot, and then translates all of the robots all of the blocks in the world to the robot's frame of reference. And if there should be a block in the robot's view and it doesn't see it there, it eliminates that block from the world map. With every single movement that the robot makes, either straight line or rotational, it takes a new a new picture, and then processes that picture with every single block. And on the right side of the video, you see the world map. The blue lines are the actualized movements of the robot, and the gray lines are the planned paths from the A-star algorithm. They never line up, which is expected. The goal, though, is getting an accurate representation of what actually occurred. So after each movement, I remeasure both the heading and how far we actually went to determine the current location. And now here we have a screen recording of what I was seeing as the robot was moving through the Grand Challenge arena. So the Grand Challenge, the final test of the robot, you get 2 attempts. And if at any point the robot touches the outer wall, that's the end of your turn. There's 9 blocks in the arena, and you attempt to collect all of them. On this attempt, I actually collected 3 out of the 9 blocks. So fell a little short of the 9 block goal, but collected some good information and then made some tweaks to the code in an attempt to get more blocks in the future. I reduced the amount that it orients towards each block in its collection algorithm, hoping that we wouldn't over-rotate. And another tweak that we made in between runs was that I looked at the height of the bounding box, and if the bounding box was wider than it was tall, I determined that the block had tipped over. And then for my second run, I would no longer target that block. I would go look for a different block that was still upright, because once the block was tipped over, there was really no shot that you were going to get it picked up. unless you somehow manage to roll over it and upright it. So for the second run, running some untested code, a little nerve-wracking. It's not something you ever really want to do, but desperate times, desperate measures. And we were hoping for a better run. So now this is our second run. Again, running some untested code, hoping for some better results. Let's see what happens.
There was another time. So always 2 runs.
Oh. Massive bummer. Oh well. You can actually see in the world map here that the robot had the right idea of where it needed to go, but for whatever reason just drove straight into the wall. So we didn't collect all the blocks. Bit of a letdown, but these things happen. I was actually aware that that bug existed in the code base. I'd seen it a few times where in my testing, the robot just like wouldn't follow the path that it had laid out for the first step, but it would track and it would know that it was off course. So I was never able to catch that bug. It was really intermittent. And Murphy's Law, it just struck again. But hey, oh well. Want to say thank you to Dr. Mitchell. Great course, really enjoyed myself. Great time. Thanks for putting this all together. I really feel like I learned a lot. And yeah, thank you for watching. On to the next semester.